The next assignment is to write a sniffer and a parser. The first part is about capturing an entire IP packet in its raw form. And the second part is about analyzing its content, parsing it according to the rules, and visualizing it in a very human-readable form. So, you remember that the first thing inside the header of an IP packet is the version number. How many bytes are in there?
Wait, bytes?
Yeah, how many bytes?
Half a byte.
Half a byte. So it's 4-bit long. Yeah. But when you operate with data in your computer's memory, the smallest unit is a byte. In the sense that if you have a variable, you can't have a bit. Even if you use only 1 bit, it still takes 1 byte. So let me represent it here. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 bits, of which the first 4 are the version number. So we need this part. And let's say that x equals to this number. How do we get the first 4 bits?
By shifting to the right.
By shifting to the right.
4 times, and it's going to just remain the 4 bits.
4 times.
Yeah, 4 times.
Okay, so in this case we could say version equals x shifted right 4 times.
Yeah.
And if you look in its contents, it will be 1, 2, 3, 4, preceded by 1, 2, 3, 4. Where did these zeros come from?
From shifting.
When we shift, that's filled with
Yeah, so when you shift it to the right, whatever was used to be there isn't there anymore, so it's filled with zeros. Now, let's say that these bytes, these bits were A, B, C, D. What happened to them?
Gone.
Exactly, they are gone forever. Okay, now let's say that A, B, C, D actually contains something that I need. So my question is, how do I get just that part out of X?
Mask.
Someone said mask. Is there anything else? What if we try to use the same primitive? What kind of a different shift?
Arithmetic shift.
So you mean this?
Yeah.
You refer to the type of shift without loss. Okay, you could also do it like this. Shift it 4 times to the left, then shift it 4 times to the right again.
Yeah, we still lose half the data.
But we don't care about this. We
Oh,
only
so
need
then
that
yeah, you
part.
could shift.
It's just taking a little bit longer and it's not elegant. So someone said mask. What kind of a mask is it? Do I have to put something on like this?
Yeah.
All right. How does it work?
We end a logical end made between our x and 0f representation in hex of a number.
Okay. So you said 0f.
Yes, in hex.
And I'm going to use the 0x prefix. It means this thing is in hexadecimal. And if you convert this into binary, then what is it?
0, 0, 0, 1, 1, 1.
1, 2, 3, 4. 1, 2, 3, 4. And then you said that I have to do a binary AND between this and that.
Yep.
So let's try it. So A, B, C, D. and is 0 when one of the operands is 0, so obviously this part is discarded. And is 1 if both operands are 1. So since this one is always 1, then the result of this depends on A, B, C. So it will be like that. A, B, C, D. And this, of course, is 0, 0, 0. So now, if we look, let's say this is called Y, then Y is equal just to that without the first 4 bits. So, we did this very simple manipulation to get access to the version field of an IP packet, and whatever the 4 bits beyond the first 4 bits are. This is how you would be able to access them. In the same fashion, you can extract the data from other parts of an IP header and store them in some humanely named variables, and then display those variables in a very user-friendly format. However, there will be some complications. For example, at some point in an IP packet, there is a field called source address, which in the case of IP version 4 is 32-bit long.
Yep.
So my question is, how will you extract this number?
Well, the IP packets all have a width of 32 bits, right?
Well, I could represent it as one long line.
Yeah. Yeah, but
The 32-bit bound is
They-
just for
yeah, but the
visualization.
information is usually separated into the 32 bits. Like if we cut off in pieces of 32 bits, it's not gonna cut off to the middle of a valuable piece of information, right? It's not gonna.
Well, it depends on how you slice it. I have to remind you that whatever we use here, you know, a nice representation where this bound is a 32-bit,
Yeah.
it would be absolutely the same if I drew one long line.
Yeah, yeah,
So when you say you count the data,
At
the cut
32
is
bits.
only in your mind.
yeah. But when we slice it at exactly 32 bits, we don't slice any important data. Like we don't go to the middle of a data and slice it in half. We always slice it at the exact end of one of the data fields, let's say.
Yeah.
Well,
Either that or for
let's say
IPv6.
this is the source field,
Yeah.
and I could cut it here.
No, you can't.
Why can't I? There is no
Because-
force in the universe that will prevent me from, let's say,
Well,
this is my raw data,
yeah.
and I could access from offset 4 to offset, let's say, 8.
Yeah, yeah, you can do that.
Slice it any way I
Yeah.
want.
You can do that, but I said if we slice it at 32 bit, like the exact case, not 32 bits, but like if we take offsets of 32, like pieces of 32, then we're not going to overlap our source because we all take from the initial 0, and then we cut in 42 parts, like 32 bits.
Okay, it makes sense. So what you're suggesting is that we will just get this entire chunk,
Yeah,
and then we could slice it in 4 individual bytes,
if
convert those bytes
if we
into
need
numbers,
to, yeah.
and then display them as, let's say, A.B.C.D.
Sure, if we need to, yeah.
And this ABCD has nothing to do with this ABCD. It's just
No,
an unfortunate coincidence in the name choosing. All right. But what if you had some format where you had to retrieve a bigger number? Let's say it's one big 64-bit integer. How would you get that as a number?
Into integer.
Depends on the language.
What did you say?
It depends on the language we use.
Uh-huh. Okay, so of course, it depends on a lot of things.
Oh, also, yeah, there could be a long variable that has 8 bits, a long int, but I mean 8 bytes.
Okay, what about some super customized thing, which is 37-bit long? Because someone's favorite number was 37. So they devised a protocol where you need to get something which is exactly that many bits long.
Sure, we're still gonna put in a container bigger that's an exact number, like say 64. We're still gonna put those 37 bits in a 64-bit container, and the first from the left, the first bits are gonna be 0.
Okay. So in Python, there is a very handy module called struct,
Yeah, structures.
which allows you to interpret raw data in different forms. It's really, really useful. And when this is over, I will show you a quick demo on my computer. So we focused more on this part, but let me tell you a few things about this one. The question is, how do I get the whole IP packet? So far, when you made your socket object, you would only receive the payload, the application layer data. But in this case, we need to go deeper and get the whole thing, not just the payload. And you can do that using raw sockets. I won't explain how to do that, because if you go to Python's socket module documentation, there's a sample right there at the end. You can just run it as is, and it works. So your mission is to figure out how to make a socket object that gets the whole IP packet, receive one of those packets, and keep it in some variable, let's say P, packet. And then you would have to parse this buffer according to the rules defined in the RFC, and show me not just some mumbo jumbo on the screen, but nicely displayed as version equals something. Source address equals something else. Destination address equals some other thing. So you have to parse every field and show it to me in a very nice, beautiful format. Yeah?
We have to pass just the UDP, or we're gonna have to handle all the possible transmission layer protocols that's under it.
Okay. You only need to parse the IP header, and its payload could be represented as mumbo jumbo.
Oh, thank you.
Because, you know, there could be a lot of things in that payload, and if you parse everything, it will be a complicated task. Whereas in the context of this assignment, I have two objectives. One of them is to teach you how to do something with raw sockets, and the other one is to teach you how to write a parser for a protocol such as IPv4. There is a difference between this and what you did with Quick Chat. In Quick Chat, they're not using bits, individual bits, or they're not using individual bits to represent something. So you either operate with a byte, or it has some keywords, like in other protocols. For example, in the POP protocol for receiving email, when you connect, you send the word user, I think, with the username, then the word pass with the password, then, let's say, then you send the word list to get a list of emails in your mailbox, and so on. So these are commands which are human readable ASCII strings. In the case of this parser, you will be able to, well, you will be forced to deal with low-level stuff. And this is a different type of experience. So two basic objectives. Learn how to use low-level sockets, and learn how to implement a parser and get some exposure to this module if Python is your language of choice. There is a function called setSoc op, which can get a bunch of input arguments. One of them says, I think you pass it a flag. which is equal to that, sock underscore raw. A few minutes ago, someone asked about multicast. This is the way you do this. You rely on set sock opt with some other flag which corresponds to multicast. I don't remember the exact values, but they are documented somewhere. Though I do have to emphasize that doing multicast is not trivial, because in this example, at least in Python, there is a sample in the manual which you copy and paste, and it really works. In the case of multicast, finding a sample that works might be challenging. So what are your questions for now? Is it clear what needs to be done? Okay, I'm glad to hear that. I just have to add a few more twists. Besides parsing the raw structure, I might add a few more requirements, such as if the payload encapsulated in the IP packet is a UDP datagram, then make a beep or something. It's nothing serious, but it's different from what people did in the previous years. Okay, this is just to ensure that you can't just copy and paste stuff that happened a couple of years ago. And another thing you could do, or another thing I could do, is say that instead of parsing IP version 4, you will parse IP version 6.
But aren't we gonna do that anyways? Like, we don't know what IP packet is gonna fly towards us.
That's a good question. Now, I mean, that's an interesting observation. When you make that socket,
You can specify something.
whether it's IPv4 or IPv6. So remember, when you make a socket object,
Yep.
you pass it a flag option which
Yep.
says AF INET.
That's IP4?
Yeah,
Oh.
I think there's INET 6 or something along those lines, which explicitly says I want IP version 6. The only problem is why I'm not making this a mandatory requirement is because some people might be using operating systems that don't have an IPv6 stack.
Yeah.
So, I mean, if I enforce this, I would be, by definition, hurting some people. And remember that the local host address for IPv6 is that. But, you know, if you think about it, the IPv6 header is simpler than the IPv4 header.
Yeah.
It's less of a headache.
Yeah, but if you have to work with both of them, you're gonna have to make a check in the version before you actually put the
Yeah.
data in the structure.
In the first version, I mean, in version 4, this will be equal to 4, and the other one it will be
Also
equal to
4.
6. No,
No, the version.
I'm okay.
No, I
It
mean
says
the
4 bits, but I only place my finger under the number 4.
Oh, okay.
So it's still 4-bit long, but the
Yeah,
value is 6.
Yeah,
Okay, so if you have no more questions, then we switch to the demo.
Is there any third-party libraries that can do parsing? I mean, or it's done manually? Or
I'm pretty sure there are
a lot of
such libraries out there, and your fellow students from the previous years have written such parsers. But in this case, the point is to actually do it on your own. It's an exercise in, you know, sharpening your parsing skills. It's not about just showing me this. If I wanted to see that, I would just start Wireshark. This is just a side effect of the fact that you implement the parser on your own. And for some people for whom Wireshark was unable to capture broadcast traffic, like in your case, generated by Quick Chat, there's a workaround. You can use Microsoft Network Monitor, which is a sniffer written by Microsoft for Windows. That one displays all those packets. And what happened in the previous years is that students got these assignments in a different order. They first implemented the sniffer, and then they reverse engineered Quick Chat with their own sniffer. And
Nice.
some people actually did it and it worked. So for those who desperately want this done without Microsoft Network Monitor, for bonus points, you can roll out your own sniffer and then sniff quick chat and prove the world that you can do this. Any other questions? Well, in that case, let's switch to the practical part.